it does is takes a red-black tree, we'll call it T1, and another red-black tree, T2, and some element, which we call X, such that for all A in T1, A is less than X, and for all B in T2, X is less than B. So I'm just saying that everything in this tree is less than X, everything in this tree is greater than X. And what we want to do is merge all of the numbers in both of these trees and X into one red-black tree. And we want to do it efficiently in logarithmic time. Alright, so the first thing we're going to do is just slightly tweak red-black trees so that we know at all times the black height of the red-black tree. And that's actually pretty easy. We just store a number at the root, being the black height. And whenever we get to the case where we fix invariant 3, by coloring a node from red to black, then we increase the black height by 1, right? That's the only time where we increase the black height. So we can keep track over the course of the life of a red-black tree what its current black height is. And also, if we do a traversal, if we walk down the tree from the root, we can keep track of the current black height very easily now, right? We just start with the total black height, and then if we cross a black node on our walk down, then we know that the black height of the subtree that we're currently at has 1 less black height. If we pass a red node, then the black height doesn't change. So that's all just to say that we can assume that we always know the black height of the node that we're currently looking at. Okay, so we're going to make an assumption that K1, which is the black height of tree 1, is greater than or equal to K2, which is the black height of the second tree. And I'm going to present a solution for this case, and the solution for the other case where K2 is greater than or equal to K1. It's basically the same, it's symmetric. But so we're going to assume that this tree has a bigger black height than this tree. So this is T1. Now what we're going to do is find the node with the largest value that is black and has black height K2. So there is such a node. If we look at this path here, this is called the right spine of the tree, we know that at some point there's going to be a black node with black height K2. And it's going to be bigger than every other black node with black height K2. We can have a whole bunch of other ones over here. They're all black nodes, they all have black height K2, but they're going to have lesser values because they're further left in the tree. So let's just call this node Y. And what we're going to do is, well, let me draw what we do. So basically we break apart tree 1 at this Y node. We take out the Y y subtree. And then we're going to make it the left child of our x node, the new node that we have there. And then we make the right child of the x node t2. Yes, so first of all we need to check, is this a binary search tree? So we know that everything in T2 is greater than x, and we put it to the right as the right child of x, so that's fine. We know that everything in T1 is less than x, so we're allowed putting anything from T1 to the left of x, so this is all fine. And yeah, since we know x is greater than everything in T1, then making it the right child of something on the right spine is also valid. So this is all a binary search tree. And now we have to check all these invariants too. So are all the leaves at the same black height? So that actually depends. We put in this new node here, so I still have to decide what color should I make it. So if I want property 1 to still be true, which color should I make it? Did someone say something? What?
I said red.
Yes, that's right. So if you make a node red, then you do not change the black height of any leaf. So that's fine. Property 1 still holds. Property 2 might not hold that now though, right? Because what if this node here were red? Then we have a violation. But we know how to fix these, right? So we can just apply this fix-up procedure, and that has to potentially walk up to the root in log n time to fix up. And yeah, so the root is black. We're not making any changes to the root unless x is the root. X could end up being the root, right? This whole thing be empty. In which case we would just color x black, and then we're done. Yeah, so I think that's everything. And as I said, there's the other case where K2 is greater than K1, and then you just get a symmetric situation. This T1 is T2 minus Ty is Y. Yeah, something like that. So you're just working the left spine instead of the right spine. Any questions?